Okay, I was muted. Hi. Now I'm assuming you can hear me. I'm going to be recording this, so I can post it online just like before. Yeah, thank you, everybody. So we can keep track of attendance. What's up? Not much, just studenting as usual, you know. So today we're going to go over worksheet 15. And again, I'm going to be assuming you guys have looked at it already. And I'm just gonna go over it. You can stop me if you have any questions, as usual. Okay, so yeah, worksheet 15. First problem is just giving you a bunch of substrates, and like this, alkene is a substrate, and it gives you reagents and other conditions. Thank you. It asks you to draw the product or show the products. So I can go over the mechanism if you guys want me to, and I probably will, but like if a question doesn't specifically ask for the mechanism and you know what the product will be, you don't really have to do the mechanism. It's kind of just like showing your work. I mean, now that we're all doing stuff online, I'm not sure how he could ask you to do that, but suppose you were taking it in person, doing the mechanism would be like showing your work. So like if you were doing 2 + 3 on a math test, you could just say the answer is 5, but like you could show your work. I mean, that's a dumb example, but it's like the analogy of doing a mechanism. Yeah, I'm gonna not do the mechanisms unless you guys specifically ask me to, especially because these are things that we've looked at before. So like when you have water and this is just an acid catalyst, that just adds the OH to the Markovnikov spot, which is here because that has more substituents than the other spot on the double bond. And that's a common theme with pretty much all the reactions for question 1. You get a Markovnikov product. It's like here, there's 2 spots that the bromine could attach to. Again, I'm not going to do the mechanism unless you guys want me to. Just gonna show the product. It goes on the Markovnikov spot, which is where the methyl group is, because that has more substituents. I'm gonna erase the board to make more space. Did he end up finishing chapter 8, I think, is what you guys are looking at today? Thank you for letting me know. No? Okay. And I did that poorly. Is he gonna have all of the chapter on the exam? Did he tell you that? Because it's cutting it kind of close at this point. Oh, shoot. Okay, well, anyway, he might not have said anything, so that's fine. But yeah, right after spring break, I know. Yeah, 1 more lecture. That's why I'm trying to figure out what's going on, but you might not know. That's okay. So in regards to this question, I specifically put A2 on the reagent, the hydrochloric acid. So we're adding 2 equivalents. So that means it can react with both the double bonds here. So this one and this one. So for the one on the left, it's gonna attach to the Markovnikov spot, which is here. That's secondary versus primary. It would be here. That's why that doesn't form. And then on the right, the chlorine, it's chlorine. It attaches here because that's tertiary versus primary. Again, the Markovnikov spot. So if there's a 2 on the reagents, then you're adding 2 equivalents and it can react with 2 double bonds or whatever else you happen to be looking at. Okay, so here you're reacting hydrobromic acid with this, and you can basically ignore this entire benzene ring. Like, we're not going to react with it. You're not going to be doing any reactions with it for a while. So it's just there. You could almost just picture this like this. It would basically be the same in terms of what you care about for the problem. So for the product, the bromine attaches to the Markovnikov spot again, which is here. That's the tertiary position compared to secondary here. So hopefully this is getting a bit redundant. That's part of why I'm not doing the mechanism, because it would just bog us down. Okay, so I'm gonna move on to part E. Right, so here I put a 2 on the hydrochloric acid, the reagent, but again, we're not reacting with the benzene. And there's only one double bond, so the 2 is more or less just a trick, I guess. It's gonna react just the same way as if you only put one equivalent of hydrochloric acid. So the chlorine will attach here, and you're not gonna get like an extra chlorine here or something. That's not gonna happen because there was only one double bond. You can't just add another chlorine just because, well, there was only one double bond. That's why. So hopefully that makes sense. Just don't react with benzene and don't react hydrochloric acid with an alkane. Thank you. Yeah. Okay. So now the last part of number 1. So don't want to sound like a broken record too much. It just adds the chlorine to the Markovnikov spot, which is here, because that's tertiary versus secondary up here. You guys notice. So I'll move on to, and I have no idea how he'll ask a mechanism question on an online test, but I'm sure at least one will come up in some form or another. So even if you can't draw mechanisms, which I do recommend being able to do because it helps you figure out a product, but you should at least be able to like identify what the mechanism should look like for the reactions that you have to note for. There are some that we kind of gloss over because it's just too complicated. It's not really necessary, but for some you should know. So like adding HCl or HBr to an alkene, you should know this mechanism, and we've done it a bunch. So for hydrochloric acid, the first step is the nucleophile, which is the double bond attacking the hydrogen from hydrochloric acid. We get an intermediate, the hydrogen attached here on the less substituted spot. And we get a carbocation here, and that forms because it's tertiary, it's more stable. And then the chlorine ion attacks carbocation. And we get this product. So that is something we should be comfortable with because we've done it a lot. But the next couple are at least a bit more new to you guys. So if you have any questions, feel free to stop me. But yeah, I'm just gonna go over it. So here we have cyclohexene reacting with Cl2 and CH2Cl2. So like a general thing, I guess, stuff on top of the arrow, like the Cl2 here, that's a reagent. So the stuff on top is generally like what's reacting with your substrate, which is this, it's an alkane here. And then the stuff below the arrow is generally just like a solvent or a catalyst. So CH2Cl2 is just a solvent. It's like reacting salts and water or anything else you might have done in Gen Chem. It's just like you generally used water, but with OChem, things aren't soluble in water, so we use other stuff. But that's just like a general thing. Like basically all you really need to worry about is the stuff on the top. The stuff on the bottom is kind of just there, and you can ignore it for the most part at this stage. Okay, I'm gonna erase that stuff to give myself a bit of space. But that is something I think is important to know. So for reactions with Cl2, it helps to draw it like this. And chlorines have free lone pairs. So the start of the mechanism is a little weird, I think. Like the alkene is acting as a nucleophile, and at the same time, the chlorine is kind of acting as a nucleophile. It's kind of hard to say what one or the other is, but basically like a sort of ring forms here with the electrons flowing back and forth, and then this bond is broken like I showed. And I think you went over this in class, but I'm doing it here because practice helps. Okay, so it doesn't matter if you do dashes or wedges. I'm gonna do dashes. And I don't think you really have to show stereochemistry for the intermediate, but I feel like it helps a little bit. So the chlorine is bonded to both carbons, and it didn't look like he did it with his notes, but when we get to one of the other reactions, I think this will help understand things. Okuda taught it by putting like the positive charge within like this sort of triangle ring here. So the positive charge is like shared between this carbon, and the chlorine. And that kind of explains like the Markovnikov addition of a hydroxyl group later, but we'll get to that. But for this reaction, it's just two chlorines, and here it doesn't really matter where it attacks, but let's just say it attacks this carbon, then this bond breaks. And that's the only intermediate. So then because that top bond broke, like the chlorine down here has the dash, and then the other one has a wedge. And it's important that they have opposite stereochemistry, so they're trans to each other. And when the product is trans, you call that anti-addition. That looks kind of like a D. That's my bad. So if they're trans, that's anti. Then that's stereospecificity. That's a term for these reactions. Okay, so moving on to C. I should have put CH2Cl2 here. I don't know why I put Br. I don't think that's a solvent. So that was my bad. Not that that affects the problem too much or at all. So again, you have the lone pairs. It's kind of helpful to draw them in. Direction starts with these arrows flowing back and forth. Okay, so again, stereochemistry doesn't particularly matter. It helps to indicate it going one way or the other. And I put the methyl as a dash because the other thing is the wedge going towards the bromine, but you could have made the methyl a wedge and the bromine a dash. You have the positive charge in the middle. And then the other bromine comes and attacks here, and that breaks this bond. Okay, yeah. Wait, did I mess that up? Okay, well, they should be opposite. Sorry. Yeah, I probably could have done that better. Kind of watched that, but the mechanism's a little weird with two bromines, I think. It's easier with hydrohalogenation. Okay, yeah, I should have put this on the wedge. No. Okay, I'm sorry. I'll just redraw this substrate here. Down here is a wedge. Yeah. Thank you, Jared. So they should be opposite to each other, and the bromine here should be cis to that methyl group. Like, that's not something you should memorize. I'm just saying, like, that's a note here. What's important is the two bromines are trans to each other. So again, it's anti-addition. I was just trying to, I don't think I did the arrows here fully properly, but like, what's important is a bromine comes and attacks one of the carbons and that bond breaks, and then you get anti-products. That's the main takeaway here. This helps. I haven't practiced this as much lately, so that's probably why I'm making mistakes, but if you guys practice, you'll do better than I am right now, and you'll be okay. Okay, so now we have chlorine and water, and the thing on the bottom now is important because the solvent is water and that will react in a reaction. But the first step is the same as those last two. It's just the Cl2 reacting with the double bond like this, forming a sort of ring. Okay, so I'm gonna give them wedges. And the positive charge, like I was saying, is kind of shared between these free atoms here. And because of that, you can remember like when we were adding HCl and HBr, the Cl attacked the more positive cation. So, I mean, not the more positive, the more stable. And if we were to look at the cations that would form, there would be one here or one here. So this is secondary and this is tertiary. So the water comes and attacks what would be the more stable cation, which is the tertiary. That's why it attacks here, and then this bond breaks. So this is a wedge, this is a dash, and this water is positive. Should draw it out a little differently to make this easier. So we had a, that's something I forgot, this bond breaks. And the chlorine that was formed before comes and takes that hydrogen, and then the electrons go to oxygen. So you form HCl. That's not super important, but it's like a byproduct. And this would be the product. So the hydroxyl, the alcohol, attacks the Markovnikov spot. So the reaction is Markovnikov for OH. And then it's again anti-addition, and the mechanism is nearly identical to adding Cl2 or Br2. So the anti-addition is something that should be easy to follow, I think. Does it matter the orientation of the wedges or dashes? Do you mean does it matter if you drew these like the thing on the left or the thing on the right, or do you mean like what direction the dashes and wedges are going in? Like that's one too many. Are you talking about drawing it going down like this? Or like, it doesn't particularly matter if you were pointing more towards something like this with the dash pointing down instead of up. I think it helps like when you're looking at this step here, if you draw the ring kind of going towards an easier to visualize spot, but it doesn't particularly matter, I think. You just have to show that you understand what you're drawing if he asks for a mechanism. But whatever makes it easier for you to do is probably best. Okay, so that's that. For E, so we're adding water. H3O plus is an acid catalyst, and heat is just a condition. So this reaction is similar to adding HCl and HBr, and you've seen it before. I should redraw that like this. So the double bond takes a proton from water, just like taking a proton from HBr. Proton attaches here, and we get carbocation. Actually, this is the acid catalyst. That's a little detail, but yeah. So now water comes in and attacks the proton just like a Br minus ion or Cl minus. Hopefully you guys are noticing that there's a lot of patterns with these mechanisms. They have some parallels, so you don't necessarily have to memorize things multiple times. You can just remember one of them, you'll be good. Main difference between this and adding HBr is the intermediate. The water that gets added has a positive charge, so that's why another water comes in, takes the proton, gives the electron to that hydroxyl group, and then you reform the acid catalyst, which I'm not gonna draw, but that's what happens. And the OH added to the Markovnikov spot. That's number 2. I honestly thought this worksheet was going to take longer than it did, but hey, that I guess means you guys don't have to sit around for as long. Right, moving on to number 3. So I asked, will the products from number 2 rotate plane polarized light? Why or why not? So I'm just gonna go over, I guess, well, B, C, and D aren't the best choices. So I'm gonna go over A from the last one and just point out what's important. So we saw this already. That's the first step. Okay, so again, hydrogen attaches here, and there's a cation here. And do you guys, okay, so like, what is the hybridization for this carbon and this carbon? That's important. Is it sp3, sp2, or sp for these two? Yeah, they're sp2. And what is the geometry for sp2 carbons? Trigonal planar, yeah, so the planar is important. That means that it is flat. So I'm gonna draw a carbocation. It'll look, this is sort of a 3D representation. The dashes mean it's going like into the page or the screen, and the wedge means it's coming out. So if I were doing this in person, I'd show you a model, but I'm sure you can find pictures on the internet, but this is like sort of a representation. And then this is the empty p orbital for the sp2 carbon. It's empty because there's a positive charge. So the p orbital is like both above and below the carbon. So when that chlorine comes in here to attack that cation, it could either do that from the top or from the bottom, and it doesn't really care because it's like it's a flat molecule. It could just as easily do it from the top or the bottom. So when this happens, you'd get some of this. And you'd get some of this. You'd get both stereoisomers. So these are enantiomers of each other, and you'd get basically a 50-50 mixture of the two. And there's a term for that. It's racemic. I might be spelling it somewhat wrong, but you get a racemic mixture. So because you got an equal mixture of the two, the rotation of light cancels out and it doesn't rotate light. So like this exact question he probably wouldn't ask, but he might ask, what's the geometry of a carbocation intermediate? Or what's the hybridization? And you tell me, or you tell him what you just told me. The hybridization's sp2, the geometry is trigonal planar. He might ask like what the product mixture would be like, and you might say it's a racemic mixture. Like, these are all questions you could theoretically ask. So that's another reason mechanisms are important. They help you identify stuff like this. So hopefully that made sense. I'm just gonna add a planar. So yeah, hopefully that makes sense. Okay, and number 4 is just showing products given conditions and reagents and such. And you guys hadn't learned many reactions last week, so I don't have much here, but depending on what you were given today, I can probably just come up with some more problems to fill the time. So for A, we have NBS in water, and I didn't put it, but probably have DMSO. Do you guys know what NBS, what its purpose here is? Well, Jared said no. Does anybody know what it's here for? Okay, so this, in the lab, BR2 is kind of nasty. You should have, yeah. He might have glossed over it, but you should have last week. So NBS is a source of BR2 because BR2 by itself is just a nasty reagent, but NBS basically gives BR2 in a less annoying way. So this is very much like it's the same thing in terms of like writing a mechanism and drawing the products as putting BR2 in water with an alkene. And it's the same reaction as Cl2 in water. So if you see NBS over water, just think of this reaction, BR2 in water. So that means that I'm gonna draw the product down here, and I can show the mechanism if you want, but it's the same as adding water and Cl2 to an alkene. And what you make a dash and what you make a wedge doesn't necessarily matter. What's important is that the BR and the OH are trans to each other, because this is an anti-addition. And then the OH goes on the Markovnikov position, so OH is Markovnikov. So yeah, NBS is just a source of BR2. That's something you should commit to memory probably, because he should have covered it. I saw it in his lecture notes. He might have glossed over it, but it is a reaction he can throw at you. Okay. For B, this is just, Cl2. So again, like I'm just gonna draw the product and I can show the mechanism if you want, but it's the same mechanism I showed in number 2, just with a different substrate. You should still show the stereochemistry, even though like this carbon here isn't chiral. It's still important to specify like the 2 chlorines are trans to each other because this is anti-addition. So that's just something I think you should do if you had to draw this. It's relatively straightforward. I've seen it before. So I'll move on to C. C was something I'm guessing you guys saw today. You hadn't seen it last week. when I posted this, but I think you could figure out what the product is just by looking at the reagents and thinking a little bit. So we're adding H2, the palladium catalyst. It's just a catalyst, basically. It just makes the reaction go. So when you have H2 over PDC, just all you're doing is adding hydrogen. I'm not writing very well, but we're adding hydrogen. You don't have to know a mechanism for this, but it literally just adds hydrogen. So here, like there's a lack of hydrogens because of the double bond. So now there are hydrogens. Did he go over this reaction today, out of curiosity? Yes, okay. Did he talk about the stereochemistry? No. Well, I'm gonna show you it, and if he never covers it, then you probably don't necessarily have to know it, but these two are cis to each other. The hydrogens that get added are cis, and when the stereochemistry is cis, that's called syn addition, SYN. I don't know why it's called syn, but that's just the term used for cis products. So yeah, just H2 over palladium or a platinum catalyst would just add hydrogens. Okay. So for D, just like before, the benzene is kind of just there. You can ignore it. So we have water and H2SO4, which is just an acid catalyst. Not giving myself much room, so I'm going to draw the products down here. So this reaction, like before, is just Markovnikov addition of the alcohol. It's not too bad. If there are no questions, I'll just go on because we've seen it before. For E, okay. Did he go over this last week? I'm hoping he did. Either last week or today. Yeah, this, okay. This is oxymercuration, demercuration. You don't, at least you shouldn't have to know the mechanism for this, but like the steps that happen do help follow what's happening. So I'm gonna give like a summarized mechanism, I guess, similar to what he gave you probably. Actually, off the top of my head, I probably shouldn't do this, but like, I'm not gonna do the electron pushing, but I can show like the intermediates at the very least. At least some of them. I'm pretty sure that's what happens. And then we have acetate. ion kind of just floating around. And I believe a water attacks one of these. Was this the substrate? Oh yeah, they're both secondary, okay. So this is all that first step, the HgOAC2 and the water and THF. And if you were to do this on a test, like if you didn't put the 1 and the 2, like if you just wrote it like this, like I have it right now, you'd be saying that you put all of that stuff into like a beaker or a flask or whatever at the same time, and then you probably wouldn't get the product you want. So that's why it is important to put the 1 and the 2, because if you don't, then it's wrong. So don't neglect the numbers, putting things in the right order. So okay, so the water is added, and then a proton probably gets abstracted by the acetate. I'm not gonna show that, but I'm just gonna, like, since I pointed it out, you guys know that is what I would have drawn. And then at this step, that's when NABH4 comes in, and it basically just puts a hydrogen here and takes away the mercury. You don't really have to know why. And I'll be honest with you, I don't know why. I never really learned the mechanism for this because we didn't have to. But the NABH4 just takes away mercury. And because of the stereochemistry we had here, this is also where the intermediates end. If you didn't cover this detail in class, you probably don't have to know it, but the hydrogen and the alcohol are trans to each other. So this is anti-addition again. And because both of the spots here were secondary positions, it could just as easily have added the alcohol here because they're both equally stable. But this reaction is Markovnikov, which the next problem shows for F. So I'll go over that now. This time I won't show all those extra steps. I'll just show the product. And if any of you were wondering what THF is, it's just a solvent. It's kind of just there for things to sit in and react. And it's mainly the water and the mercury acetate that are important here. So the product, like I was saying, is Markovnikov added alcohol. And if you wanted to show the stereochemistry, then the alcohol and the hydrogen have trans stereochemistry with each other. So yeah, that's this reaction. And then number 5, just a bit of practice with drawing things given a name. Again, I don't know how he'll ask this now, but it's possible it'll come up in some form. So the thing for A is E 3-methyl 2-pentene. So you can, I guess, start by just putting a 5-carbon long chain. And then it says there's a methyl group at number 3, so I'll put that. We can give the numbers. And then it says there is a double bond starting at carbon 2. So this could potentially be drawn incorrectly, and if it is, then I would erase it and fix the stereochemistry, but we can check that now. So it says it's E with the double bond. That means that the higher priority groups are opposite of each other. So on the left, there's a methyl group and the hydrogen. The methyl group gets higher priority. On the right, this ethyl group gets higher priority than the methyl. So on the left, it's pointing down. On the right, the higher priority is pointing up. So they are opposite of each other. So that is E. And this was correct. So those are the general steps I'd take if I was asked to draw something given a name. Just do the skeletal structure, put the substituents down, put the double bond, and if it turned out that this was wrong, then I did it again, but you could just put it like this. And now both of those are facing the same direction, so this would be Z. So you just go from making it look like it's normal to putting a bit of a kink where the double bond is. And that'll flip the stereochemistry. That's more or less what I would do. It's the same as like if you're doing RNS, just flip the dash to a wedge. It's the same idea. Okay, so for B, it's 2Z, 5Z, free methyl, 2,5-heptadiene. So it says heptadiene, so there's 7 carbons. It says there's a methyl group at carbon free and a double bond at 2 and 5. So if we look at the double bond here, this is pointing down and this side of the molecule is pointing up. So this is E, that's not C. So this is wrong. And also at this double bond, this is pointing down and this is pointing up. So again, they're pointing opposite directions, they're E. So basically the structure was wrong, but we can redraw both of the double bonds like this. That looks bad. And now both of these are Z configuration. This is pointing down, this is pointing down, so that's cis. This is pointing up, and this is pointing up, so that's cis. Or we could look at the hydrogens on this one, and they're both pointing down. So this is the structure for B. Hopefully you guys practiced that before I showed you, because I think it's easy to mix up drawing E and Z. So just, if you're not comfortable with this, practice, that's what I'd recommend. That's everything I have in my worksheet, but I can do something like this for those of you who want, I guess. Like, I don't know how far he got today. Actually, I don't even remember off the top of my head, so maybe I shouldn't do this right now, but I was thinking I could come up with some problems for you guys to do. I don't know what reactions he got to today. I do only have 20 minutes, so it's not even that much. So I could just end early, unless it's all good. You gotta wait until Thursday, that's probably a better idea. And I can look into what he's done. I can do a review session I don't want to do it over spring break because I feel bad, but like your test is the day of my workshop, so I can't really help you after whatever you cover on Thursday. So I probably will do a review session of some sort, either on Friday or spring break. Thank you. Oh, he didn't annotate it. Okay. Before you guys go, I am curious how far you got. I'm looking at his notes right now. Like, what was the last thing he covered, I guess? Did he get to, shoot, there's a lot here. He has chapter 9 here. Well, he definitely didn't get there. Okay. Carbine additions, yeah, that's what I was thinking he got to. So he's almost done with chapter 8. He'll probably get into chapter 9 on Thursday. Okay. I'll just have problems for those on my next worksheet. I'll have as many reactions as I can come up with, I guess, since the more practice, the better. And the cleavages are kind of tough, so actually I can, nobody's left, I can go over some cleavages right now. I think that is useful. Wait, did he go over cleavage? I'm not seeing it in his notes. Where though? I mean, I see epoxides, I see diols. Oh, okay. 16. So, okay. I can just use this substrate. So, one cleavage you can do is with O3, which is ozone, in one step, and then the second step has, I should redraw this, that looks terrible, but it's zinc with acid. So we're just cleaving the double bond, and I can draw it cyclic or as a straight chain. I'll probably do cyclic first. But basically, like, you can draw the substrate as it was, but now, like, this double bond that was here isn't here anymore. That bond is broken. And in the place of the double bonds, you add carbonyl groups. If it's at the end of a chain, like, well, not at the end of the chain, but like if there's no substituent like a methyl group, like on this carbon here, this has just 2 hydrogens versus, or 1 hydrogen, and this one had a methyl group. So this forms an aldehyde if it's at the end of a chain, and if there is a substituent like a methyl group, it forms a ketone like it did here. You could also draw it, I'm gonna count. You could draw it like this, theoretically. I think I might have put too many carbons actually. Yeah, it did. I think it's easier, especially when you're starting to practice these, to draw it like this, but it's perfectly fine to draw it as a straight chain like this. Just make sure to count your carbons when you do, like I did. I had one too many and that would have been wrong. But this has Oh, it still has a, what? Okay. That's my bad. It's not as easy. It's not as easy to count these when I'm doing it virtually. It's 3, 4, 5, 6, 7. So like I was saying, aldehyde and ketone. And I'm gonna erase this. The other cleavage you can do with the same substrate. And I guess after this, I'll just end it because I don't want to come up with too many problems off the top of my head, but you can have, actually, I'm gonna look in the notes to make sure I don't put the wrong. Did you not cover this? Oh, you did, okay. So you have KMNO4, and acid, and this again cleaves the double bond. So you get a ketone up here again. This is looking a bit weird, but instead of an aldehyde here, you get a carboxylic acid at the end of a chain. So KMNO4 is a pretty strong oxidizing agent. That's why it adds an oxygen where there was an aldehyde. That's how I remembered it, because you're going to see KMNO4 come up again and again over the next year. So just recognizing what it does now is a good idea. It oxidizes things. So that's why there's a carboxylic acid formed. I'm going to have probably several cleavage problems because they're kind of tricky, but that'll be next time. I'm just going to stop talking here and let you guys go because I've already gone over my worksheet and a little bit extra. So thank you for coming and listening to me. If you have questions, feel free to ask, but otherwise, you're free to go.